Welcome to this video on oscillatory motion of a pendulum. In this video we're going to be taking a look at the pendulum in a little bit more detail so that we can set up a approximation for when we have a non-simple pendulum, or what we call a physical pendulum. So first of all, here I have a pendulum that's at some angle theta away from its equilibrium position that I've shown like this. And what we want to do is take a look first at what we would call the restoring torque in this situation. So just like the restoring force, this restoring torque is going to restore it back angularly to its equilibrium position. And we know that we can find that value by doing F cross R, which would be the restoring force cross the R value, the lever arm, the distance from the axis of rotation, which is right here, to where the force is applied. Now the force that's being applied is the vector, or is the force mg, and we know that only a perpendicular component of one will point to the other. So if I extend out the r value here like this, I see that this theta angle is the same as this one. And so what I'm really looking for is this component, and this component is opposite the angle. So this component is going to be mg sine theta. That's the component that's pulling it back towards the center. And just as a little side note, the tension in the string is actually going to end up being mg cosine theta, which is this piece over here. Now, the string has a length L, so what I'm going to do here is go ahead and factor that into this expression as well. So I'm going to say the force is mg, and we're looking at the component that's perpendicular to R, which R, remember, is equal to L. Now I also know that restoring torque, or torque in general, is going to be equal to the moment of inertia, or the rotational inertia, times the acceleration, the angular acceleration. So I can go ahead and set those two expressions equal to one another. Now I know that the angular acceleration, if I wanted to change this into a differential equation, this would be the second order differential equation like we talked about before. This is going to be d squared theta over dt squared. So when I substitute this in here, I'm going to end up with something that looks like this. Now, at this point, I'm going to go ahead and look at the moment of inertia, and then we're going to come back and do some other things. Now the moment of inertia, or the rotational inertia of this situation, where the mass of the string is so light compared to the mass of the object, that we can really consider this mass of the object as the thing that's rotating about this axis of rotation. And so we're considering it to be a point mass. Okay, so all of its mass is located at the end of the string L, and so we know that that is our equation mr squared, which in this case could be ml squared. So I'm going to go ahead and factor that in here, or substitute it in. So I have mg sine theta L equals ml squared times the second derivative of the position with respect to time. Now it becomes clear that the mass factors out, and we saw that in our experimental evidence that the mass had no bearing on the period of this situation, and we're going to look at that in a bit more detail in this video. We're also factoring out one of the L's over here, and so what I'm left with is g sine theta, and I'm actually going to divide this L onto the other side, so I can have my constants together. So I have g over L sine theta equals d squared theta times dt squared, so the second derivative. Now this over here is what we refer to as a nonlinear second order differential equation. And that's a problem because this does not show simple harmonic motion. So let's put it on hold for a second and rather take a look at a situation that's going to be specifically a simple harmonic oscillator. Remember, that's where there's a linear relationship between the force and the displacement, or the acceleration and the displacement. You can look at it in either way. Right now, they're not. Now it turns out we have this really nice approximation that we can make. So here I have a graph. Let me make this a little bit smaller. I have a graph, and I'm going to graph y equals sine of x on this graph, and I'll try to make it as pretty as I can. Okay, so we have y equals sine of x. That's not very pretty, but it'll do. And then I'm also going to graph y equals x. Okay, now y equals x is just a straight line. Y equals sine of x, of course, oscillates back and forth. But we can see that for these first few values over here, the two functions have the same output. So y is the same value between these two functions. Now I drew them not overlapping, just a little bit so you can see them, but you can imagine them laying right on top of one another. So basically what we can say is, for small values of x, so these small values of x, the two functions have the same output. So what I could say then is that the sine of x is really just equal to x at those small values, or we could change that to the sine of theta is really just equal to theta, or the displacement for those small values. Now, as soon as we start to diverge here, we see that we can no longer have that linear approximation. So if I go over to this situation and I look at what physically is happening here, it's really this, right? This only works for small angles. So this is a simple harmonic oscillator when I have a small angle that's starting. And what I see is that effectively the period's going to be the same no matter what angle I started at, as long as the angle is a small angle. So what I'm going to do here is adjust my function to be g over L times theta equals d squared theta dt squared. And this now is a linear second order differential equation. Now that I can solve, and I know the general solution of that because we came up with it before in the last few videos. And so let's go ahead and just write the solution in here. We would say that theta, the angular displacement as a function of time, is equal to the maximum theta value times the cosine of the angular frequency times time. And you could add plus v for the phase shift, but it's not essential. Now we saw that the angular frequency over here was equal to root g over L, which is the gravitational field times this length. And that we saw didn't cancel out when we set up the differential equation. So we could factor this into the situation here and then solve for the period. However, if we had a situation where one of two things were different, either this angle was not a small angle, or there was actual mass to take into account that was distributed along this line, then this would no longer be the function that provided the position at any given time. In this case, we'd have to go back to our drawing board, and the drawing board would be somewhere over here. Now if we think about it, if the angle was not small enough, the first thing we would not be able to do is this step from here to here where we said sine theta was approximately theta. That would be a no. We would not be able to do that, and therefore we would have a non-linear second order differential equation, and this kind of equation would actually have a solution that is not a closed form solution. So it would have to be solved numerically, using a computer or some sort of program to solve it. So that would be our first issue, and we would no longer be considered a simple harmonic oscillator. Now an easier issue to solve, or a way we could write out an expression, is, again, if not all the mass were at a position fixed away from this, but it was spread out, obviously I would be a different value, and I would have to include I in my final expression here. I wouldn't have been able to factor out the mass and a dimension of the length. So you could see that the mass would actually affect how much the pendulum's period was. And we can take a look at that in our next video.